Hello, chemistry. We're about to dive into chapter 13, section 2. And this section is all about colligative or colligative properties of solutions. You can say it either way you like. And these are properties that depend not on what they are as much as how much there is of what there is. So here's the definition. Properties that depend on the concentration of the solute particles, but not their identity, are called colligative properties. So colligative properties depend on how much is dissolved into the solution. Now, you might recognize this little chart here. Solid, liquid, gas. This is our phase diagram. The reason why it should look familiar is you can find it back here on page 335. And you can see at the solid, liquid, gas, these different phases. Well, colligative properties are going to change these. So depending on how much is in solution, this line is going to move. So let's take a look at that. So on this phase diagram, you'll see that this is the original freezing point line. So at 1 atmosphere, water normally freezes at 0. But if we put in something into the solution, salt or sugar or something, it's going to lower the point at which it freezes. It will no longer freeze at 0. Now, of course, if we change the pressure, that line is going to change, similar down here as well. Also, normally at 1 atmospheric pressure, water will boil at 100 degrees Celsius. But if you add a solute to it, salt, sugar, something like this, it's going to increase the point or raise the point at which it will start to boil. And so we call this freezing point depression or boiling point elevation. Now, before we go any further on those words, we need to understand a little bit about what's called vapor pressure. And this is talking about a non-volatile substance. Volatile simply means that it wants to evaporate easily because there's very little attraction between molecules. Whereas water, there is some attraction, so it's not very volatile. It doesn't want to evaporate very easily. So a non-volatile substance is one that has little tendency to become a gas under existing conditions. Now, pure water would like to boil and evaporate at 100 degrees Celsius. Below that, it won't boil, but it still wants to evaporate. Now, what if we put something into the solution? The reason why it dissolved was because there was attraction between the particles. I want to take you a few pages back in your chapter to this diagram as a reminder, page 426. And you can see here salt, sodium chloride is dissolved in here, and all the water molecules are making a sphere around this chloride ion because they're all attracted to it. And same with the sodium. They're all attracted to it. Well, if there's this attraction going on, is it going to require more or less or the same amount of energy to go from the liquid phase to the gas phase? Well, it's going to take more energy to break these guys apart. So the more sodium and chloride that we have dissolved into the solution, the more there's going to be attraction of these particles, the less likely it wants to evaporate. And you can see this even here with the sugar. Even though it's a non-electrolyte, these water molecules are very attracted to the sugar. They don't want to leave, so they're not going to want to evaporate. And the more of these sugar molecules we have in the water, the more water molecules attracted, and less likely they're going to want to evaporate. So when they say equilibrium vapor pressure, we are considering this balance of evaporation versus condensation. And by putting a solute into the solvent, we shift the equilibrium vapor pressure towards the liquid and not the gas.